Welcome to the 2018 NASA Ames Summer Series. This year, the Summer Series includes a variety of topics, from actual missions, results from laboratory work, to proposals that may be a future mission. The disciplines carry and cover a wide array of topics. I like to look at it as from Earth to space and back to Earth. How you see the world heavily depends on the tools you have to help you interpret what you see. Today's presentation is entitled Adaptive Optics for Astronomy, Achievements and Prospects. It will be given by Dr. Claire Max. Dr. Max is a professor of astronomy and astrophysics at the University of California, Santa Cruz, and is the director of the University of California Observatories. Her current research, from the title, you could tell, and interests include adaptive optics and laser guide stars to improve astronomical images. Prior to working and getting a job at UC Santa Cruz, she was a physicist at Lawrence Livermore National Laboratory. She received an AB in astronomy from Radcliffe College and a PhD in astrophysical sciences in the field of plasma physics from Princeton University. She is a member of the National Academy of Sciences. She has received numerous awards, including the Ernest O. Lawrence Award in Physics by the U.S. Department of Energy, the James Madison Medal of Princeton University, the American Astronomical Society's Joseph Weber Award for Instrumentation, and so on and so on. In addition to the numerous publications, she continuously contributes both to the scientific field and educating the next generation of scientists. Please join me in welcoming Dr. Claire Max. Thank you very much.
Okay, welcome to you folks. How many of you are interns? Fantastic. All right, we're good to go here. Can you hear me okay? Good. Let's see, where's my little pointer thing? There. I'm going to talk about 3 topics, introduce you to what adaptive optics is, and what astronomical advances it has allowed to date, and then what does the future hold. And for those of you who don't know very much about the field yet, which you will very shortly, adaptive optics allows telescopes on the ground to see as clearly as if they were in space, at least at infrared wavelengths today. And so I want to talk both about new AO systems for the future, AO is adaptive optics, but also what do I see as being the future synergy between telescopes on the ground and telescopes in space? And it's a very interesting story. So the basic issue that adaptive optics tries to address is that turbulence in the atmosphere limits the performance of ground-based telescopes. And you all know that turbulence is the reason why stars twinkle. And a hint, my husband sometimes jokes that I'm removing the twinkle from the stars. But more importantly, turbulence spreads out the light from a star, and instead of being point-like, it becomes a fuzzy blob. And that's what we're trying to fix. Now, this is a really extreme situation, which I didn't even realize till I started thinking about it. How many of you have looked through an amateur telescope, maybe the sidewalk stargazers or your uncle or, yeah. So those were probably 8 or 10 inches or smaller. Maybe sometimes the biggest ones are 16 inches. And turbulence means that even the largest ground-based telescopes, as big as from one side of the stage to the other, see no more clearly, have no better spatial resolution than a little backyard telescope. And that's pathetic. So that's what we're trying to fix. This is an example of what you see with your eye, but also with a CCD from a ground-based telescope. And this is all oops, sorry. How do I go back? Here we go. Don't quite have this yet. So you can see how turbulence distorts the image, and it also blurs it out. That's the only point I'm trying to make with this slide. This is an image of a large scene, but if you're trying to make an image of a point of light, you can see more quantitatively what adaptive optics does. So this is just a picture of a star, Arcturus, a bright star, with a 1-meter telescope. And if you take a long time exposure, the image is almost round, not quite, and it's about 1 second of arc across. That's an angular measure. However, if you take images that are so short that you're freezing the effect of the turbulence and you're just looking at one incarnation of the turbulence, which of course changes with time, it doesn't look like this at all. It looks like a bunch of dots or speckles. And if you take a lot of them and add them up in a long exposure image, they roughly end up round. But they're not round at any given instant. And what adaptive optics does is it tries to gather all these little speckles together and pile them on top of each other. And it's all done with mirrors, and I'll show you how in a few minutes. So broadly speaking, adaptive optics is a way to correct optical distortions of any kind. Could be distortions that are caused by things besides the atmosphere. To improve image quality. It lets you reach angular resolutions that are at what's called the diffraction limit of the telescope. So if you have a telescope of diameter big D, and you're observing at a wavelength of light lambda, the angle in radians that is the smallest angle that you can distinguish with that telescope is the wavelength divided by the telescope diameter. And that's a fundamental physical limitation. And what adaptive optics lets you do is to get from this big fuzzy blob to something very, very close to the diffraction limit, lambda over d. And it's applicable in astronomy, and I'll show you in a little bit at the end of the talk some other applications as well. This is just to illustrate that. This is a very blown up and very slowed down image of a star. That doesn't look much like a star, but if you imagine averaging all those blobs over many, many frames, it might get more round, would get more round than you see here. And so there are two things happening. One is you're spreading out the light, but also the centroid of the motion is wandering around. And so you have to correct that as well when you're trying to fix this whole thing. So without turbulence, big telescopes will always see more clearly, have better spatial resolution than small ones. So if I have two sized telescopes here, a little one and a big one, the image of a distant point source, because a star is so far away that it's almost a point, is the image taken by the telescope is bigger with a small telescope and smaller with a big telescope. And that's simply this equation that I showed you on the previous slide, that the best you can do in angular size of this dot is the wavelength divided by the diameter. So big diameter, small angle. And that's what we're trying to get to on the ground. We can do that in space, and it works great. And we'd like to be able to do that from the ground as well. So I just wanted to say a few words about, sorry, losing my voice here. About why turbulence in the atmosphere blurs out images that you are trying to obtain with your telescope. So parenthetically, I don't know how many of you have discovered this so far, but when you get a lecture on adaptive optics, light always comes from the left. Don't ask me why. It doesn't come from the top, doesn't come from the right, comes from the left. So here, the star at infinity is way over here. The light is propagating through millions or billions of light years of interstellar space, and it has a perfect phase front when it reaches the top of the atmosphere. So what is a plane wave? These are surfaces of constant phase. You know that light is a sinusoidal disturbance in the electric and magnetic field. And a surface of constant phase just maps where all the peaks or the valleys of the waves line up as you look on a plane. And if they all line up perfectly and make a flat plane, it's called a plane wave, but it's also perfectly, basically a perfect wavefront for you to deal with your telescope. But when that light reaches the top of the atmosphere, it encounters little index of refraction variations due to the temperature differences in the atmosphere from turbulence. And by the time it gets to the bottom, that wavefront is distorted. And I've greatly exaggerated, of course, how much the distortions are. You may have learned in optics that if you have a wavefront here, the rays, which are the direction that the energy is going to propagate, always are perpendicular to the surface locally of the wavefront. So that means that the energy is propagating this way on this part of the wavefront and a different way on another part of the wavefront nearby. And that has very important implications. So here is what happens if you have a perfect parallel light rays coming from a plane wavefront. You focus them, and it comes as close as possible to a point within lambda over d. If the light rays are affected by turbulence, as I said, the directions of the rays are changed. So this one is going a little bit that way, this one's going a little bit that way. And when you try and focus them, they don't all focus on a point because the assumption of your optics is that they were all going to come in parallel, and they're not. They're sort of random angles. And so you get this blurry image here. Okay, so how can you correct this? Here's a cartoon of how we do it. This is your favorite galaxy. You want to get an image or a spectrum of your favorite galaxy. And the way you do it is if there's a bright star near your galaxy, you can use the light from the star to measure the turbulence hundreds or thousands times a second, because of course it's always changing. And then the telescope, at the back of the telescope, you put a very fast detector that does the turbulence measurement quickly. You calculate on a computer the shape that you have to apply to a special mirror behind the big mirror of the telescope that changes its shape hundreds or thousands of times a second. So this is a mirror, I'll show you in a minute. It's a mirror, the simplest form is a thin sheet of glass. It's got little actuators glued to the back. And each actuator, when you send a voltage to it, gets a little longer or a little shorter, and it pushes and pulls on the surface of the glass. So once you've sent the signal to it, the light, both from your favorite galaxy and this guide star, if they're close enough, the light goes through the same turbulence, and they're both corrected, and you can take your image or your spectrum. This is slightly more technical version of this. Now the star is way up here. The telescope is up here. The light from the telescope after the main mirror is still distorted, but you have this adaptive mirror whose wiggles are kind of opposite to the distorted wavefront. And after the light bounces off the mirror, it's mostly corrected. Nothing's perfect. It's not corrected perfectly, but much better than it started. And you want to be able to keep tweaking it so you can get as close as possible to a perfect correction. So you steal some of the light with a beam splitter, measure the wavefront again, and send the signal back to your mirror. But most of the light goes through pretty well corrected, and you have your high-resolution camera or spectrograph to look at the result. This is called a closed-loop feedback system, feedback control system. So you're always correcting just the difference between a perfect wavefront and what your deformable mirror did on the last time step. So it's called a null-seeking control system. You almost have a perfect correction, but not quite, and you're always dialing in what the next correction should be. And of course, there's at least two things happening. One is your measurement wasn't perfect in the first place, so you're trying to fix it. But also, the turbulence up here changes with time, so you're always playing catch-up. And those are the two things that this closed-loop control system is trying to do. And I just want to remind you that in this picture, the light has already gone through the telescope, so you're not wiggling the main mirror of the telescope. And you can think about why that might be. The main mirror of a telescope weighs tons. It's this thick or that thick. And you just can't wiggle it at 500 or 1,000 times a second. It's too heavy, too thick, and not flexible enough. So you have to do it with another mirror. So here's that same image that you saw before, greatly blown up, greatly slowed down. This is the image with adaptive optics. Right away, you'll see two things. One is it's not perfect. If it was perfect, all the light would be in just a few pixels. But there's a little light that doesn't get corrected. And also, it changes a little bit with time. The atmosphere is changing. You're always playing catch up. But there's one thing that I've hidden in this portrayal of these data, which are real data, and that is in each of these two panels, the white pixel is the brightest pixel in the whole image. So that's the brightest pixel in this image, but this pixel actually contains much more energy than that brightest pixel because I've gathered all the light from this huge area and put it in just a handful of pixels. So this shows you the overall effect of adaptive optics, but it doesn't show you the key thing, which is that you've got, now this is intensity versus X and Y on the sky, and without adaptive optics, this is that same image, you have just these little speckles. With adaptive optics, you've taken all this big area and put all the light in just 3 or 4 pixels. And so the intensity goes way up in those 3 or 4 pixels. And why would this matter? Well, let's imagine that you're looking at a nearby star and you think there might be a planet around the nearby star. And you want to get an image of the planet. If you don't do the adaptive optics correction, is that the planet? Is that the planet? Is that the planet? You can't tell the difference between a speckle and a planet. But if you've gathered most of the light into these few pixels out here, which is where these guys are, you can clearly see a planet that's up to 1 million times fainter, if you try hard, than its parent star. And the goal is to get even more contrast between the planet and the parent star. OK, so I thought I'd tell you how these deformable mirrors work. This is very much a 0th order approximation, but here's the mirror in side view, and here's a very idealized / fake wavefront of light coming in from the left. And instead of having little wiggles, I've given it one big notch aberration just to illustrate how the mirror works. Now, I've made my notch in the deformable mirror, but only half as deep, literally in distance. Why is that? Because the light's going to come in, and it's going to go out again. And what you're trying to do is make the part that's in front travel farther than the part that's in back so that the part that's in back will catch up. And so you make the light travel both in and out, that's the factor of 2, and afterwards you end up with a perfect corrected wavefront, at least in this approximation. This is very idealized, but an actual deformable mirror isn't that different in concept. Here's your thin sheet of glass. Here are your actuators, not shown as little voltage leads that tell each actuator how to expand and contract. And you're doing the same thing. You're making the part of the wavefront incident wavefront that's in front catch up, be caught up by the part that's in back by making the part that's in front travel farther. So it's just optical path difference that you're adding. I have to emphasize this is greatly exaggerated in terms of the amount of deformation that you have to put. The amount of deformation put in by our atmosphere is typically the wavelength of light or slightly less. So one of my big disappointments when we built the first adaptive optics system at Lick Observatory was we were running the adaptive optics system, and I thought, oh, I'll go climb a ladder and look down on the deformable mirror, and I'll see it wiggle. I heard that it was going. It makes sort of a clacking noise, but I couldn't tell anything with my eye. It's just such a small change that the atmosphere induces, and yet it's a huge effect that we're trying to fix. OK, so let's talk a little bit about what these deformable mirrors are like. This one is about 30 centimeters across. It's got 1,000 actuators glued to the back. And you can sort of, this is before the reflective coating was put on the mirror, so you can look through the glass and see where the glue is. You can imagine a little grid here. Each one is an actuator. So that's about this big across. This one is the size of a postage stamp or less, has the same number of actuators, 1,000 roughly. It's made by the same technology that you make computer chips, photolithography, and it's what's called a micro-electromechanical system, because each of these 1,000 little actuators creates a tiny little electric field that pulls down on a membrane, a surface membrane. Then you have great big ones. So here's a much larger deformable mirror. This one's upside down, but the general idea is with modern telescopes, you have light coming in from the stars. The light bounces off what's called the secondary mirror and goes through a hole in the primary mirror to reach your detector, or sometimes it's turned sideways and reaches your detector over here. And so if you make this mirror adaptable, you don't have to add any extra mirrors into your whole optics, and that's good. You want to keep it simple. And so here's an adaptive secondary from the University of Arizona. And again, instead of these tiny little leads, electrical leads that you see here, there are these giant cables because they have to make big actuators push and pull on this fairly thick mirror by comparison with the thickness of the other mirrors. So we tried this out. We built our first adaptive optics system at Lick Observatory. It was by no means the first adaptive optics system in the world. The Europeans had one running in Chile. There was one running in Hawaii. And so we built one at Lick, and then which is near San Jose. And then on top of Mauna Kea in Hawaii. Keck is a segmented telescope. So when you get to be 10 meters across, the weight of the glass, if you made a monolithic piece of glass, is so heavy that it starts to sag. And it's complicated to support, and it has to be thick enough that it has some material strength. And so my colleague Jerry Nelson came up with the idea of making these little hexagonal segments and controlling them very carefully so that it acts as one big mirror. And so again, as we saw before, the light comes in from the heavens, goes up to the secondary mirror, and in this case, it could either go through a hole in the primary or it could be sent sideways to one of these things called a Naismith focus. Someday I'll try and find out who Mr. Naismith was. This is what the Keck primary mirror looked like. We're looking at it head on. It's parked sideways. And it's before that last row of segments was added. You can see that there's not much of a gap between the segments. Here's one segment, here's the next segment. You can also see that this is a person, so this is big. And I wouldn't want to be sitting where he's sitting, but that's good. Fortunately, I don't have to. Okay. What we did was we put our adaptive optics system at Keck on one of these Naismith foci, so the light comes down, up, and then to the AO system. So this is an early type of result from adaptive optics at Keck. Similar results were obtained on other 8 to 10 meter telescopes in the world. This is the planet Neptune. It's about 2 seconds of arc across. And the Keck telescope is 10 meters across. Without adaptive optics, there's your fuzzy blob, except you've fuzzed out an actual detailed image, not just a point of light. Hubble does much better. Of course, if you can get above the atmosphere, that's wonderful. You don't have to deal with any of this. But it's hard to launch 10-meter telescopes into space. And so Hubble is a 2.4-meter telescope. And just this is what you're seeing here is Neptune with its circumferential cloud bands and polar cap of clouds. But it's limited by the fact that this is just a 2.4-meter telescope. And if you can make a 10-meter telescope operate at the diffraction limit, this image should be 4 times sharper than that one, because this is 4 times bigger than that. And in fact, that's exactly what we found. So for the past decade, observations at infrared light, for example, between 1 and 2.3 microns wavelength, adaptive optics on these big ground-based telescopes actually gives better spatial resolution than Hubble because the diameter is bigger. It's simple. But there are gotchas. The field of view is much larger for Hubble than it is for an adaptive optics system. And you can imagine why that would be. If you're measuring the turbulence in this direction, but you have a wide field of view, by the time you get to the edge of field of view, you're not looking through the same turbulence anymore. Or the way to say that is in that picture of the favorite galaxy and the guide star. If the favorite galaxy and the guide star light aren't going through the same turbulence, you're not going to get much correction. So space telescopes have this huge advantage of having a large field of view and also of having ultraviolet light and far infrared light, thermal infrared light that don't get through the atmosphere at all or don't get through the atmosphere very well, much more capable in space than on the ground. But I put this up here because I want to emphasize that this is a very narrow field. This is a couple of seconds of arc across. And in the coming decade, we're seeing, in fact, already much wider field adaptive optics systems. I wanted to say a little bit about the heritage of adaptive optics historically, because I think it's an interesting story of threads from both the astronomy community and the defense community crisscrossing over several decades as time went on. So adaptive optics, as far as I know, was first discussed by Horace Babcock, an astronomer at Carnegie Observatory in 1953. But of course, in 1953, we barely had fast digital electronics, much less we had no fast digital detectors. There were no deformable mirrors, and so it was a hypothetical suggestion, but very hard to implement. And in the late 60s and 70s, Lincoln Labs and the Air Force, military and aerospace, actually did make this happen, first analog and then digital. There were also, in parallel, early experiments in the university context. Louis Alvarez's group at Lawrence Berkeley Lab did a feasibility experiment. They had instead of having a 2D deformable mirror, they had a line of actuators, and they corrected the turbulence in one direction only. So they made things that were skinny in one axis and fat in the other axis for stars. But they showed that it could work. And then in the 80s, lots of things started taking off. So the Air Force telescopes went digital and put in really capable adaptive optic systems, and astronomy started having these feasibility experiments. And it was in the mid-90s that many facility class AO systems were installed on ground-based telescopes. Facility class just means they have to operate for all the users every night. You're not tinkering with them and optimizing them all the time. It just sits there and works. It has to be serviceable by people who aren't necessarily super experts. An interesting aspect is that the emphases of these military and astronomy adaptive optic systems were somewhat different. The military always wanted very high performance. And so they were looking at bright targets. For example, they were imaging satellites, which were in sunlight, which are bright. And so they could use all that light at high signal to noise to get to very high performance. Astronomy is always going for the lowest light levels possible. Things are very faint up there. We can only see with our eyes a few thousand bright stars. After that, it's all over. You need big telescopes. You have to integrate for a while. So that makes it tough. We're always pushing how low can you go. And then we want to be able to look anywhere in the sky. I mean, your favorite galaxy is someplace else than your favorite galaxy, and we want to be able to look even if there aren't bright stars nearby. Okay, so that brings us to the next issue, which is if there's no nearby star, you can actually use a laser beam to make your own star. So that's called a laser guide star or artificial beacon. And what you do is you shine your laser light up to about 90 kilometers in the case that I've been involved with. And I'll show you how that makes a spot of yellow light in the atmosphere. And it's close enough to infinity that the light from the guide star at 90 kilometers is almost as good to use as a reference as a star that would be off at infinity. And so that's what we've done. And So first at Lick Observatory, then at Keck Observatory, we have these cute laser beams coming out. And that's how you get full sky coverage. So you don't need to wait for a bright star to be near your favorite galaxy. You just point the laser at your favorite galaxy and you're done. Just a few words about how this happens. There's a layer of atoms up at about 90 kilometers in the atmosphere, which are due to meteorites burning up in the atmosphere. We call it a meteorite, but that's kind of glorifying what this thing is. They're little things that aren't much bigger than a dust grain that are coming in from outer space, hitting the top of the atmosphere. And when they get to this height, their friction with the atmosphere is enough that they get hot and they ablate away, and their atoms manage to stay in this layer for a while before they diffuse down into the rest of the real atmosphere low down. And so in particular, what we've done is used sodium atoms up here. There's also iron and potassium and calcium and all that, but sodium has a beautiful ground state atomic transition, for those of you who know what that is. And when we shine yellow light at a wavelength of 589 nanometers onto this sodium layer, we can make it glow yellow, and that's our artificial guide star. So it's not a point of light. It's about this big at a height of 90 kilometers, and that's small enough that when you look at it with a telescope, it can act like equivalent to a point like a star would be, because you're looking at it from a large distance. So I think I'm going to skip. Well, maybe I won't skip this. I'm showing this is my UFO slide. It doesn't look like it, but it's my UFO slide. So when we first got into this, we decided we had to first show that it would work with an existing laser, or nobody would let us build a laser at their telescope. You know, you want to do what? You want to bring a laser to my telescope? So you got to first demonstrate that you can measure the turbulence. So I was at Livermore at the time, and there was a big laser in a building over here that was used for something else, and it happened to go into a tunnel underground to go to another building, and we, at a manhole cover, we put a big mirror in that sent the laser light straight up and didn't let it go to the lab where it was supposed to go to. And we tuned it to this yellow line that would make the sodium glow up here. And we fired it into the air. And this is where the UFO comes in. You think I'm joking? I'm not joking. This is really bright. So we had to have the local police and highway patrol and citizens know ahead of time that we were going to be firing this yellow laser, or else everybody would get all upset at us. So we carefully explained to the press that this was aiming at a solution for astronomy. And we even had a California Highway Patrol officer with us as we looked with this little telescope at the spot of light up there. So he would know when we're firing the laser in case people called in and said, what's going on? You know, he would be, it was a he in that case, he would know what to tell them. And most of the times that we fired the laser, there was a woman who lived in Pleasanton, which is about 8 or 9 miles away, who would call the local highway patrol. In fact, she would call all the 911 numbers she could find, one after the other. And she would say, there's a UFO up here, and it's shining a laser beam down into the Lawrence Livermore National Labs to suck up the secrets and bring them back to outer space. And we actually heard her once on the CB radio. She was dead serious. She was completely convinced. What other explanation could there be, right? And so pretty soon this got to be somewhat of a joke of the highway patrol people. They tried to take her somewhat seriously, but so we started hearing them over their CB radios making, you know, oh, there's that lady in Pleasanton again. We'd better prepare for the UFO to come and so forth. But that was my experience with the UFO. Anyway, this is the real thing. This is what the laser initially looked like at the Keck Observatory, which is this 10-meter telescope. You're looking at it, the mirror from the bottom here. And this was a nice example of a joint project between a national lab and an observatory, which hadn't been done all that much in the past. But today, every 8 to 10 meter astronomical telescope has adaptive optics, and almost all of them have laser guide stars. So, you know, somebody once told me that it takes a long time for new technology to penetrate and to get used by a large fraction of people. And I said, no, you know, it's not going to take that long to get this used. It's so obvious. And he took me aside and he said, Claire, washing machines in the US took 40 years to really get widely used when they first came in. Don't get worried if your technology doesn't catch on right away. So it took 15 years. That's better than washing machines, so I can't complain. Okay, but now, as I said, most of the telescopes, the big telescopes in the world have laser guide stars. This is the summit of Mauna Kea, and you can see 3 of the telescopes. There's another one over here that has a laser. And it's at least getting to be more routine than it has been. So I want to take a breath and start just giving you a quick tour of astronomy advances that have happened because of adaptive optics. And I'll give you one solar system example, an example from the center of our galaxy, and then the work that I've been doing on nearby colliding galaxies. So this is the planet Uranus. I showed you Neptune before, but this is Uranus in visible light, half a micron wavelength with Hubble. And this is Uranus at a different time. It's not exactly the same weather. With Keck in infrared light, 2 micron wavelength. And I'm showing this for a reason. The wavelength of light is about 4 times smaller with Hubble. And the diameter of Hubble is about 4 times smaller than Keck. And so lambda over d, wavelength divided by telescope diameter, is roughly constant. So what we're seeing here is that with adaptive optics, at a wavelength of 2 microns, we get about the same spatial resolution as Hubble did at a ½ micron. And as I'll say a little bit later, that's been a fantastic synergy all along, is that infrared observations with the big glass on the ground and exquisite optical wavelength observations with Hubble actually dovetail beautifully, and there are lots and lots of papers written, research papers written, which use both to look at the same object. Okay. By the way, you might not have known that Uranus has rings, but Uranus has rings. All of the big planets have rings in our solar system. This is another example of the center of our galaxy. So the Milky Way is sort of an ordinary galaxy. One of the things we've learned over the years is that most, at least substantial, ordinary galaxies have big black holes in their centers. And we do too. And this was an effort by Andrea Ghe's group at UCLA to actually measure the mass of the black hole in the center of our galaxy. So that's fortuitously possible because there is a dense star cluster right in the region right around the black hole. And if you measure the orbits of the stars around the invisible black hole, you can reason backwards and deduce what the mass of the black hole was. Same thing with the solar system. If you measure the motions of the planets in our solar system, you can figure out the mass of the sun. It's just a gravity effect. Kepler's laws, basically. So this slide was, the black hole, by the way, GC means galactic center, is here. You can't see it, it's black. It's a pretty feeble black hole. It's not accreting very much. Every once in a while, it shows up in the infrared. But the point of comparing the natural guide star adaptive optics and the laser guide star EO is that the guide star was way off over here, the natural guide star. So the quality of this correction isn't so good because you're not looking through the same turbulence when you look at the guide star as when you look at the center of the galaxy. But with a laser, again, you can point the laser right in the center, and you see 2 things. One is you see many more stars because you can defuzz them. And if you just compare this and this, there are many more stars here. And each of the stars is smaller. So I was talking about the diffraction limit. I don't know how many of you have thought too much about the diffraction limit, but The diffraction limit for a round telescope is has a bunch of rings around the main dot that's your star. But if you have a hexagonal telescope, guess what? You have little hexagons. So when we're observing and we see these little hexagons, our hearts go pitter-pat, and we figure we're in good shape. Anyway, adaptive optics, this is now the star cluster very close to the black hole. And this is supposed to do something, but if it doesn't, okay. So these stars are going to get magically clearer as you turn on the adaptive optics. And once you see it, you can see that you can figure out the positions of the stars very, very accurately. And so that's what the GES group did. And here are the orbits starting in 1995 and going to last year, I believe. This is the black hole position. And you can see the orbits of the stars circling the black hole. And this yellow one gets very, very close. In fact, right now, it's come around its orbit again and is so close to the black hole that we're hoping that we can measure general relativistic effects, strong gravity effects, right near the black hole. So this is the SO2 star. And the result of this is they measured the black hole mass about 4 million times the mass of the sun. This is respectable. 4 million is a big number. Really respectable supermassive black holes are maybe factors of 10 or even 100 more massive than this, but I'm happy. 4 million is a good number. Okay, I want to talk about my own research a little bit. I'm interested in colliding galaxies, merging galaxies. So this is a galaxy whose name is NGC 6240. It happens to have a bright guide star nearby, so I don't even need a laser. You can't quite see it, but these two bright things here are two nuclei. So the nuclei of these two galaxies that crashed into each other haven't quite merged yet. It also has these funny tidal tails, which is what happens when you hit two galaxies together. So this is a computer simulation just to give you an idea of why that funny shape happens. Here are two spiral galaxies. They pull out these big tails as they go around each other. And that's what that previous image was like as well. So here's the Hubble image in visible light. We take the nucleus and look at it with Hubble in infrared light. And all of a sudden, we can see these two nuclei. One of them is from each of the colliding galaxies. Here's what it looks like with Keck. 4 times the spatial resolution at the same wavelength. Much better set of images, for example, here. And each of these little dots here is a newly formed star cluster that happened when the gas regions from the two galaxies crashed together and they made new stars. More than 30 of these star clusters. So one of the things we asked ourselves is, if each galaxy has its own black hole, what happens to the black holes when two galaxies crash into each other? So we spent a lot of time studying the motions of the stars around each of these two nuclei. And again, we were able to deduce the masses of the two black holes. One of them's there. That looks plausible. The other one is in a deeply obscured region where it's very dusty and we can't even see it, but we can watch the motion of the stars around it, and we can see it at longer wavelengths. So both of these two black holes are about 1 billion times more massive than the sun, this one and this one. And we've had a lot of fun mapping out what's going to happen to the black holes as they spiral inwards around each other. I want to just end by, what does the future hold? Brief fly-through of what's called extreme adaptive optics, which is meant to image planets around nearby stars. 3 different ways to get a wider field of view, and I'll just talk in general about them, and then a quick slide on doing the harder stuff, which is doing AO on the ground at shorter and shorter wavelengths of light. So we want to detect planets around nearby stars. You know, here at Ames, you are the center of the world in terms of detecting planets when they transit in front of the star in the line of sight between us and the star. But that doesn't give you a direct image of the planet. You can learn a lot, but we're interested in actually looking at the planet and being able to take its spectrum, measure its mass, and so forth. So the glare from the parent star, which has been subtracted in this image, is much brighter than the planet itself. We now know many thousands of planets orbiting nearby stars, and we want to be able to image them. Right now, we only have about 24 that we've taken pictures of. And so here's a little solar system, HR 8799. It has 4 planets, 1, 2, 3, 4. And this is a nice movie that was made by Jason Wang and Christian Marat. Over a long time period, you can actually see the planets going around their parent star. Again, the light from the star has been subtracted. And the next generation of giant telescopes, we hope, will image many more of these. I want to talk about how to make the field of view wider. As I said, we're limited right now because the farther you move from the guide star in angle, the bigger the field, the more you're not looking through the same turbulence. And so you're measuring the wrong turbulence to correct. And we want to use multiple guide stars spread out in angle to let you correct over a wide field. And here's the picture. This method is called laser tomography. So if you have one guide star, you're only correcting near the star. And in addition, it's actually worse than that. You're missing data because the light from the star is coming down in a spherical wave, and you're not even seeing the turbulence around the edges. And so by using multiple stars, you do 2 things. You get to correct a region around this star, a region around that star, a region around that star. And so you make these positions so they overlap, and then you can correct over a wider field. And also, you're not having any of that missing turbulence anymore. So it gives you a better correction. And one way to do that is if you measure the height above sea level, the turbulence strength as a function of height above sea level, there are turbulent layers. So the most turbulence is at the ground, but then there's some turbulence here at 5 kilometers, and there's usually a bunch of turbulence in the jet stream at about 12 kilometers. Sometimes that's where your plane is flying and it gets all jittery and the captain has to take it to lower altitude. So typically you might be able to correct a field of view of a few arc minutes. And I'm going to skip this because it shows it can be done. But people have done this for solar adaptive optics. So here's a region on the sun. These are granules on the sun. With regular adaptive optics, this is a good image here, but as you get farther and farther away, it gets really blurry. And when you use this method with multiple guide star spots in this case, and multiple deformable mirrors, you get a much wider field of view where there's a very good correction. And here's the same thing with a sunspot. Much better correction of this cool-looking magnetic field tracers. And I think I'll skip this because I'm running out of time. Visible light AO is one of the other paths to the future. It's easier to do an AO correction in infrared light. The wavelength's longer. But there are now successful efforts to put visible light AO on 6.5 meter telescope, Magellan. So here's a double star that you can't really see without AO. And here's a zoomed in image showing that it's a real binary and it's separated by 0.032 arc seconds, which is a very small number. So the next step is to go up from 6.5 meters to larger telescopes. And I think I'm going to skip these. Finally, to complement this, maybe I'll go back one. I can't resist. The James Webb Space Telescope. So I said that with Hubble, we can get the same spatial resolution in infrared light on the ground as Hubble gets with visible light in space. It's an interesting question whether that's going to keep playing when the James Webb Space Telescope goes up in a year and a half, because Webb will really excel in the near IR and at longer wavelength IR that don't even get through the atmosphere well. But below 2 microns, which is the long wavelength end of the near infrared, the James Webb point spread function, the image of a perfect point source, is undersampled by the detector, and the inherent image quality is no longer really diffraction limited. So we may find, and I don't know if we will, that ground-based adaptive optics on 8 to 10 meter telescopes, which are bigger than James Webb, which is 6.5 meters, has actually better spatial resolution than Webb at shorter wavelengths, even going into the visible. And so this would flip the whole paradigm that we've been using so far. And it's going to be a lot of fun to figure out where the best science is going to be when we try and do things in concert with Webb. And just final slide, these are the next generation of giant ground-based telescopes. They're called extremely large telescopes. And if AO continues to work well, and if we can do diffraction-limited imaging at less than a micron, then it's going to be really fun. Here are the diffraction limit of these 3 telescopes. And we're getting down to sort of 0.05 to 0.005 to 0.01 arc seconds, a whole different ballgame in terms of seeing extremely beautiful detail on celestial objects. Thank you.
Very good. Thank you.
What's an idea about vision?
We may get it as a question.
Yeah.
So we have time for a couple or maybe a few questions, depending on the questions. If you have a question, please raise your hand and stand up when you get the mic. Go ahead.
Hi, Claire. Very nice talk. When you're trying to reproduce or cancel the turbulence, do you go for the turbulence at the last time step, or do you approximate it using multiple previous time steps, assuming it's going to be continuing to evolve in some way?
Very good question. So if I can rephrase it, in control theory, closed loop control theory, there's a question of how you determine what the next correction is going to be. And a stable way to do it is to mostly use the current data, but to have a tailing off memory of what's happened before. So that's mostly what's done.
Well, enjoyed your talk. Very nice. Thank you. And I was just wondering, what kind of frequency range can you do the correction for? Or like time duration? I mean...
hours? I mean, is that what you mean? How long an exposure can you do?
No, I mean how fast? These actuators, what kind of frequency bandwidth they have? I mean, can you correct up to kilohertz or hundreds of hertz?
The Air Force telescopes, I think, are going at several kilohertz now, thousand times a second. Astronomy, we don't have enough light. If you go very fast, you don't measure. In each step, you can't measure as much light because the exposure time is less. So we're typically running at 300 to 500 hertz.
Hi, Claire. Thanks a lot. That was incredible. So I was thinking that gravity pulls in the particles that surround the Earth, which create the problem that you're overcoming. Do the magnetic fields of the Earth have an impact on those particles?
Not that I know of. The particles that come in from outer space are the atoms that make this layer of sodium in the atmosphere, but that's up at a height that's way above where most of the turbulence is. Most of the turbulence is down in the first 5 kilometers or so. And that's mostly, we would call it weather or something. There are weather systems, there's wind shear.
The Van Allen belts with the magnetic?
Yeah, the Van Allen belts are they have such low density that they don't really mess things up very much. Good question, though.
Hi there. Thank you for the talk. Definitely learned a lot. I was just kind of wondering if you could talk a little bit more in detail about what is the difference between correcting light that's coming from a guide star versus correcting light from your laser optics. What's the difference? Is one better than the other? Do they result in different images?
No, well, we try very hard not to have them result in different images. Let me see if I can go back to this picture here. Okay, so if we're using a natural guide star, the light is effectively coming from infinity, and the rays are parallel. So you're sampling, all the light coming down is sampling the whole cylinder of light above your telescope. And if you're using a laser, even though 90 kilometers is high, it's not infinitely high, and so you're missing a little turbulence correction around the edges. And and that effect gets worse and worse as you go to bigger and bigger telescopes. So at Keck, which is a 10-meter telescope, we can still do a pretty good job with one laser beam, but as you go either to this next generation of big telescopes or to shorter wavelengths, you're going to have to use multiple guide stars, which is sort of this scheme.
I've always wondered why planets don't twinkle and stars do.
Basically, a planet is a finite source of light, and so the rays coming from different places on the disk of the planet fill in the twinkles. I don't know if you notice I'm waving my hands.
Planar waves.
Yeah, they're plane waves.
Because they're closer, they're not planar.
The light from the planet gets just as messed up as the light from a star. But the thing that makes twinkles is when the light coming from exactly one direction does a fade because of the interference in the different turbulent cells. And so if you're getting light from a finite source, there's enough angular diversity that when the ray from one direction starts fading, the ray from some other direction is there to fill in the hole. It's not a quantitative answer, but.
I'd like to ask about the future with respect to some of the big telescopes that people hope to put in space. It's my understanding that because they're large and they may want to move around, waves pass through these mirrors, and consequently you have to correct the mirror itself. Are systems like this where you move the mirror something that's going to be important for those systems?
Yeah, that's interesting. So even with James Webb, which only has half a dozen segments or however many it is, I forgot, 7 or something, they have to be constantly measuring the deviation of each segment from a perfect alignment and tweaking it. The time scale for doing that measurement and correction is a week or two, because they do the measurement, they send the data down to Earth, people on Earth or computers on Earth calculate the correction to the actuators of the segments, they send it back up, and there's delays in t-drift and so forth. But it's a closed-loop adaptive optics system in some sense of the word. They're not changing the shape of each segment, but they are changing the alignment of the segments. And the Keck Observatory as well, on a time scale of a few seconds, they're always measuring how well these 36 segments in this case are aligned and correcting it. And people have tended to call that active optics when it's slow. But frankly, the line between active optics and adaptive optics is getting blurrier and blurrier, so to speak. And when you get to the really big telescopes in space, you're going to have tens of segments. I don't know what the number is, maybe 100, depending on what the design is. And they're going to have to be tweaked all the time, hopefully locally, rather than sending the signal back to Earth and then back up to space again. So it's either very fast active optics or it's very slow adaptive optics, one or the other.
Okay, so with that, please join me in thanking Dr. Claire Max for an excellent talk. Very good. Very nice. Thank you.
You guys are a great audience.